All right, so definitely please let me know if you have any questions at any point, especially now, about anything we've been discussing or are about to discuss today. Last time we were talking about NMR. We're going to continue our NMR discussion. We were saying how the position of the peak, or the shift on the NMR scale, which goes from 0 to 12, so here we're just seeing a section of the scale, but the position or shift of the peak, so this one coming in at around 0.9, this one coming in around 1.6, etc., that depends on the environment of the hydrogen. Right? So we're saying mostly if the hydrogen, which would normally most often be bonded to a carbon, if there's something electronegative nearby that's attracting the electrons away, that pulls the electrons away from the carbon, which in turn pulls electrons away from the hydrogen. So that's deshielding. Pulling the electron density away exposes the nucleus of the hydrogen or its proton to a greater magnitude of that magnetic field. So the magnetic field it sits in affects it more strongly when it's deshielded, and if the magnetic field is affecting it more strongly, it increases the energy gap, and that pushes it to the higher energy side of the spectrum. Right? So when we see peaks on the spectrum, if they're around 1, they're probably not deshielded. That probably represents a hydrogen that's bonded to a carbon that doesn't have any highly electronegative atoms nearby. And then if the electronegative atoms are a little closer, it shifts it down a little bit. A little closer, shifts it down a little bit more. And so we talked about where all the hydrogens might appear, and we talked about the shifts on Tuesday. We also talked about the number of signals, right? So here in this particular NMR, we have one signal here that's looking like a triplet. One here that's looking like 1, 2, 3, 4, 5, 6. Looks like a sextet. A singlet here, another triplet here. So we're going to talk about the splitting patterns today and the integrations, but typically we would count this as 4 total signals, representing 4 unique types of hydrogens in the structure. Each hydrogen with its unique environment would give a signal. If I have multiple hydrogens that are symmetrically equivalent, they're all giving the same signal. So this triplet could represent multiple hydrogens. I don't know. And that's where integration comes in. So the integration is the area under the peak. And that tells you how many hydrogens are producing that signal. So if we look at the integration, we're talking about continuing this baseline and then calculating the space under this peak. So if I color all this in carefully, the computer is calculating the area of the peak. So if the peak is very broad, it doesn't have to be very tall. There are sometimes you'll get a really broad peak. It'll have a lot of area under it. If it were tall and narrow, it might not have much area, but if it's tall, that's still all that space adding up can create a larger area. So the computer calculates this for you. Now there was a time before computers, back in the day, where the NMR would just be printed out on paper, and what chemists would do is they would grab a pair of scissors and they would cut out this peak. If they cut out the whole peak right around the line there, and then down here, if you cut that piece out and weigh it, assuming the paper is even thickness all the way across, then the relative masses of the peaks relates to their relative area. And that tells you how many hydrogens are producing that signal. So we don't have to do that nowadays. We just have the computer calculate the area under the peak, and then it produces this step curve or integration, which translates the area of the peak into a height. So the higher this step curve, this one's obviously higher here, this one's not as high, this one's a little bit higher. the height of that is proportional to the area under the peak, the space produced by the width and height of that peak. And so when the computer does that, it then asks you, it won't put any numbers on it, right? It'll just give you these step curves which are proportional to the area under the peak. So you have to, as a computer operator, when you're running an NMR, you have to then set one of these integration curves to some value. And then the computer will calculate the other values relative to that. So if I set this one arbitrarily to 1, maybe I suspect this signal is due to one hydrogen. One hydrogen on the structure is producing a signal. There are no equivalent hydrogens producing the same signal, so the signal only represents one hydrogen. If that were true, and I put that in, then the computer would automatically calculate the integrations of the other signals relative to that. And so because this peak is so tall, the area under that's about 1.5 times the area under this one, right? So it's just giving you the areas of the other peaks relative to the one I happen to set to 1. And then when I look at that, when I'm operating the NMR machine and I'm doing the integration part of the analysis, when I see that a signal represents something 0.5 roughly, that's probably not correct. I can't have this signal being produced by one hydrogen and then half of a hydrogen, roughly. Right? The molecule, whatever its structure is going to have whole numbers of hydrogens. It's not like I have one hydrogen and then half a hydrogen that are producing the signal, right? I have whole numbers of hydrogens. So at that point, if you see something like that, what you would typically do then is to double the integration and let the computer calculate the other ones at that point. And now that my values are all relatively close to whole numbers, there's always going to be a little bit of variation. It's not going to be exactly a whole number, but here I can typically round up or down as necessary. So this peak would have come from, if this peak represents 2 hydrogens, this peak represents 3, this peak represents 2, and this peak represents 3. Now it's possible that this peak could have represented 4 hydrogens. If I have a structure that's highly symmetrical and there are 4 different hydrogens that all have the exact same equivalent environments, they would all give peaks in the same exact spot and they would add together. So if this one were 4 hydrogens, then relative to that, this one would be 6 hydrogens, because it's still the same ratio, 2 to 3 ratio. And this one would represent 4, and this one would represent 6. So if I have an idea of what the structure is, I can look at the integrations and make sure each signal that I expect to come from specific hydrogens in the structure represents the number of hydrogens that signal would be produced from in the structure. So integration is pretty straightforward. It's just how many hydrogens are there of a certain type giving a certain signal. The more hydrogens there are giving a signal, the more area that signal will have. And then when you integrate the areas, the relative areas from one signal to the next tell you the relative number of hydrogens producing those signals. And as we were saying, the symmetry in the structure can impact that. So let's just look at a couple examples, make sure we got integration down. So terp-butyl methyl ether, a common solvent. We've used that a number of times in the lab. The structure for that would give you. I don't expect you to memorize the structure for types of compounds we haven't talked about yet. We've never really talked about ethers and how to name them. So if I gave you this structure and asked you where you would expect to see the signals and what their integrations would be, we're not going to worry about splitting patterns or multiplicity yet. We can talk about that a little bit later today. First I would want to do is to draw the hydrogens in. So I've got 3 hydrogens here of this type. Because there's free rotation around this single bond, all 3 of these hydrogens are spatially and environmentally, they have the same equivalent environments. And over here, there are 9 hydrogens. Each of these methyl groups has 3 hydrogens attached to it. And so on the terp-butyl side here, all 9 of these hydrogens are equivalent to one another. Right? There's still free rotation here. There's free rotation around here. All 9 of those hydrogens average out to be equivalent. And last time we talked about the replacement test. You can test that out. If I replace any one of these hydrogens with the deuterium, any one of those, we'll just put a deuterium here, versus replacing any one of those hydrogens, any one of the other hydrogens with a deuterium, they're the same structure, right? Through rotating this bond, I can put this methyl group in the same position where that one is, and then rotating this bond, I can get that deuterium in the same position where the other one is. So everything will line up and be superimposable because all 9 of those hydrogens are equivalent. So we've got 2 types of hydrogens here. All 9 of these I can label as hydrogen B because they're all equivalent to one another. So if I were looking at what the spectrum should look like here, what the signals should look like, I would have HB and I would have HA. And so where would the shift be? Well, HA is bonded directly to a carbon that's connected to a highly electronegative oxygen. And that's going to deshield HA. So we said typically a proton that's on a methyl group will come around 0.9 or around 1 ppm. But if there's an oxygen directly attached to the same carbon, we're going to add about 2.5 to 3 to that. So I expect this to come somewhere between 3 and 4 ppm. Right? We don't have to be super precise with our predictions because we'd rather give a little bit of a range and be pretty confident that the correct shift is in that range than to give an exact number that might not be correct that would throw us off in our interpretation of the data. And since the signal that we would see at around 3 to 4 ppm represents 3 hydrogens, each hydrogen gives the same signal and they would all stack on top of one another, creating a signal with a larger area for the peak, that integration would represent 3 hydrogens. For hydrogen B, where would the signal there be? Well, here I've got a standard about 1 ppm for hydrogens that are on a methyl group, and there's no highly electronegative atom right on that carbon, but there is one on the next carbon over, and so that might affect it a little bit. So maybe at most it would be between 1 and 2 ppm. I don't expect it to be shifting very much unless the highly electronegative atom is pretty close to the hydrogen. So here that's a couple atoms away. So here I would expect a signal between 1 and 2 ppm, and I would expect a signal between 3 and 4 ppm. And this one would have an integration of 9 hydrogens, because there are 9 equivalent hydrogens all giving the same signal. So that signal would probably be taller, it might be wider, be some combination of taller and wider to produce a greater area for its signal in a 9 to 3 ratio. So when we look at what that would look like on the NMR scale, which would go from 0 to 12, so with 6 in the middle, and 3 in the middle of that, I would see a signal around 3 to 4, so I'd see a signal here. And then I'd see a signal around 1 to 2, that would be much bigger. If I were running the machine, analyzing this NMR, maybe it's an unknown. I don't know what the compound is. And so when the machine gives me the integrations, and I can see one integration is clearly much larger than the other, I might set this one to 1. And this one would probably come out to about 3. Because the 3 to 9 ratio is the same as a 1 to 3 ratio. So when I do the integrations, all I really know is what the ratio is. The integrations don't actually tell me the number of hydrogens. They tell me the relative number of hydrogens. So if I set this to 1 and I see the other one goes to 3, I might think that there's only 1 hydrogen producing the signal and 3 hydrogens producing the signal. But that's not really the case. Right? So you got to be a little bit careful with the integrations. We can predict the integrations are 9 and 3 because there are 9 hydrogens of one type and 3 of the other. But when we actually look at the NMR, we really only know the ratio. if I know that the structure is supposed to be butyl methyl ether, then when I'm running the NMR, I would probably set this one to 3, and this one would come out close to 9, and that would, and the fact that they're both singlets and shifted to the correct position would help me confirm the identity of the structure. But if I don't know what the molecule is, I don't really know for sure what the integrations are. I only have the ratios. So for lab 7, when we're doing the NMRs for your unknowns, and I give your NMR spectra and I integrate it for you, I'm going to be a little bit careful. The integrations there are ratios. They don't necessarily tell you the number of hydrogens producing each signal. Any questions about that? Alright, so let's take a look at 3-pentanone. Again, another compound. We haven't talked about how to name ketones, so I wouldn't expect you to draw a structure from the name. But if I gave you the structure, and we drew in the hydrogens here to determine what the proton NMR would look like, there'd be 3 hydrogens here, 2 here, 2 here, and 3 here. So here, though, I do see a plane of symmetry that splits the molecule right down the middle. So the hydrogens of this type are symmetrically equivalent to the ones on the other side of that plane of symmetry. Right? It's also a rotational plane. If I flip the molecule over like a pancake, these hydrogens A would flip up out of the plane and land right on top of the other one, and the molecule would look exactly the same. So if rotating it or putting a mirror plane in the structure allows me to see that groups of hydrogens are equivalent, they all give the same signal. And likewise, these ones all would give the same signal. So where would those signals end up appearing, and what would their integrations be? Hydrogens A, there'd be 4 of them. So the integration would be 4 hydrogens. Hydrogens B, there are 6 of them, so the integration would be 6 hydrogens. But again, the integration, it might be 2 to 3. It's the ratio. A 2 to 3 ratio is the same as a 4 to 6 ratio. So when you get the signals and you look at their integrations, you don't necessarily know exactly how many hydrogens they represent. They just represent a ratio. So 4 to 6 ratio is what's actually in the structure. But that's the equivalent mathematically to a 2 to 3 ratio. So when you integrate the peaks, you might see one integrates to 2 and the other integrates to 3. You might see one integrates to 4, the other integrates to 5. Unless you know what the structure should be, you don't know exactly how many hydrogens are giving each signal. Now what about the shifts? Hydrogens B are on a methyl group. So the shift should be around 1 ppm. And it's a couple atoms away from a highly electronegative atom, so that's not going to affect it much. So maybe a little over 1 ppm, but pretty close to 1 ppm for the signal produced by the 6 hydrogens of type B. Hydrogens of type A, they're a methylene instead of a methyl or a methine. 2 hydrogens on 1 carbon is a methylene. And a methylene usually comes around 1.2. But this one is 1 carbon away from a CO double bond, which we said is going to add about 1 to the shift. So this one's going to appear between 2 and 3 ppm. So I'd see one signal around 2 to 3. If this were the structure I were taking in NMR for this structure, I'd see one signal around 2 to 3 that would integrate to 2 or 4, and then one signal at around 1 ppm that it would integrate 3 or 6 relative to the other signal. And the splitting patterns there would be a triplet and a quartet. We'll talk about how to figure that out in a minute after we're finished talking about integration. Any questions about integration? Alright, so the next part of the NMR that you would need to be able to analyze, and this is just for proton NMR, is the splitting pattern or the multiplicity. I usually use the term splitting pattern, but multiplicity means the same thing. So when a hydrogen is bonded to something, when that hydrogen gets hit by a radio wave, and its nucleus absorbs that energy, switching its spin alignment in the magnetic field. When it relaxes and then re-emits that energy that's detected by the instrument, not every hydrogen releases the exact same energy. So maybe I've got a whole bunch of these molecules around. Even though the molecules are equivalent, they all have the same structure, and each hydrogen on average has the same environment. If there's another neighboring hydrogen nearby, that can affect the energy of this hydrogen. So let's say there's another atom here, maybe it's carbon with another hydrogen. If the hydrogens are close enough, they can affect each other's energy. So for this hydrogen, when it absorbs energy and re-emits it, the amount of energy necessary to excite its nucleus to the different spin state can be affected by the current spin state of the neighboring hydrogen. So let's say there is no neighboring hydrogen. Let's just say I've got some structure. Let's say I've got a carbon. Let's just say I've got methane. These hydrogens are all equivalent to one another. Equivalent hydrogens can't split one another. So all four of these hydrogens are exactly the same on average, and that would produce a singlet. So when all the hydrogens are equivalent to one another, they produce a single peak. Likewise, let's just say I had this structure here. This is one hydrogen, and let's say this is bond to chlorine or something. And so in the simplest situation you could probably imagine, the structure only has one hydrogen total. There's no other hydrogens in the structure. Every hydrogen in every molecule will absorb some wavelength of energy to excite its nucleus against the magnetic field, and then when it relaxes back down to being aligned with the magnetic field, it releases that energy back out, and that's absorbed. Every hydrogen would release the exact same quantity of energy, so I would see a nice sharp singlet. Each of those hydrogens would give a signal or an energy release in the exact same spot, and so I'd see a single peak for each one of them. So we see a singlet for when all my hydrogens are equivalent to one another, or there's only one hydrogen in the structure. I also see a singlet if there's, say, equivalent hydrogens, and then maybe there aren't any hydrogens on the neighboring carbon. So let's just say maybe these are chlorine. If there's no hydrogen on the neighboring carbon, and these three hydrogens here are all equivalent to one another, they'll all release the same amount of energy, and I'll see a single peak for all three of them, right? So if they're equivalent, they show up in the exact same spot. So this scenario over here, though, which is common in a lot of structures, because if I have a chain and there's hydrogens on adjacent carbons, those hydrogens are close enough to affect each other. When hydrogens are on adjacent carbons, they're very likely to affect one another. And so what we see here is, if this hydrogen has another hydrogen on a neighboring atom, then this neighboring hydrogen, it might, at the moment in time where this hydrogen's nucleus over here is excited, the neighboring hydrogen might be spinning in the same direction as this one, or it might be spinning in the opposite direction. So in some molecules, the hydrogen spinning one way has a slight impact on the quantity of energy this hydrogen will release after it gets excited. And in other molecules, if the hydrogen's aligned in the opposite direction in the magnetic field, then this hydrogen will absorb and release a slightly different amount of energy. And that's when I get a doublet. So I see two peaks for the same hydrogen. Some of the molecules the hydrogen releases a slightly lower quantity of energy, and in some of the molecules the hydrogen releases a slightly higher quantity of energy because the neighboring hydrogens are not all in the same magnetic alignment with the external magnetic field all at the same moment in time. So if I have more neighboring hydrogens and they're all possibly splitting differently, I get these more complex splitting patterns, which we're going to talk about. So let's go through these and look at one possible scenario at a time. So this is a scenario we just looked at. So these little symbols here indicating that whatever's bonded to here doesn't really matter as long as it doesn't have hydrogens on it. So let's just maybe imagine these are all chlorines. So we have an actual structure to consider. So if this carbon has one hydrogen, this carbon has one hydrogen, actually let's make these two fluorines. So hydrogen A and B are not equivalent because hydrogen A is on a carbon with chlorines, hydrogen B is on a carbon with fluorines. So their signals are not equivalent. If the two hydrogens were equivalent, so just to point out, if I did have chlorines on each one of these positions, then these two hydrogens would have an equivalent environment. They would not be splitting one another, and each would give a singlet or a single peak, and they would both occur in the same spot. That would give me a signal that looks like this. But once I create a difference, so I don't have that symmetry anymore, A and B are not equivalent, they would start to end up splitting one another. So if I'm analyzing the signal I expect to see for hydrogen A, some of the molecules that incorporate hydrogen A, and some of those molecules, hydrogen B, will be aligned against the magnetic field. Other molecules, hydrogen B, will be aligned with the magnetic field. And so, depending on the alignment of the hydrogen B's nucleus, depending on the alignment of the magnetic field created by its nucleus with the external magnetic field, that changes the quantity of energy that hydrogen A will absorb very slightly. And so what I see is a doublet. Hydrogen B, some of the molecules, hydrogen B increases the energy required to excite hydrogen A. And so I see a slightly different signal. In other molecules, hydrogen B is aligned in the opposite direction, and it decreases slightly the energy required to excite hydrogen A. And so I also see a signal for that. And they're equal in height because there's equal probabilities that hydrogen B will be aligned with or against the magnetic field at any given moment in time. And so that produces a doublet. So let's take a look then at what would happen if there were two hydrogens of type B. And so this is assuming that these two hydrogens here are equivalent to one another. So this would be, if these two hydrogens were homotopic or enantiotopic, they'd be equivalent and they'd both be affecting A equally. So what are the possibles, what's the situation? What are the possible scenarios here? So if we're analyzing A, we want to think about how is this B going to affect A and how is that B going to affect A? This B could be aligning with the magnetic field or against. And this one could be with the magnetic field or against. So there's a couple different scenarios. One scenario is in some of the molecules during the experiment, in some of the molecules, both hydrogens will be aligned with the magnetic field. And if that's true, that affects the energy that A absorbs and releases and causes an increase in energy. Just as often as that occurs, though, there will be some times where in other molecules, both those hydrogens will be aligned against the magnetic field. And they'll both have an effect where they decrease the energy A absorbs and then releases. And so I see a signal for that scenario as well. Compared to those two, which would occur in equal quantities, there's also a scenario where hydrogen B is aligned with and hydrogen B, the other hydrogen B is aligned against, or maybe this one's aligned against and this one's aligned with. So there are two possible scenarios where one hydrogen increases the energy for hydrogen A and the other hydrogen at the same time decreases it. So that would be a cancellation. If hydrogen B is aligned with the magnetic field and it increases the energy required to excite and then the energy released when it relaxes, but at the same time the other hydrogen is aligned against the magnetic field and it decreases the energy for the excitation and relaxation of A, well, an increase would be offset by the decrease and so there'd be no change in energy. And there are two possible scenarios where that occurs. And so I see a signal associated with that scenario as well. And so that produces a triplet. Out of the four possible scenarios we described, one of those fours increases the energy, hydrogen A relaxes, the other decreases the energy when hydrogen A relaxes, and the other two cancel out, so there's no change in the quantity of energy that hydrogen A emits when it relaxes. And so that's the signal I see there. Right, so scenario 1 is responsible for this signal, scenario 2 is responsible for this signal, and scenario 3 and 4, which are the same, are occurring as twice as often as 1 and twice as often as 2, because there are two ways that that can happen. And so the area of that signal, and usually also the height of it, is twice the height of the either of the other two signals. And so that's why we get this triplet, because of the four possible scenarios, two of which cancel out any energy change. And so that's right there. That's where the center of the peak is. One extra peak when we have a slightly higher energy, and one peak when we have a slightly lower energy. And that depends on the alignment of the neighboring hydrogens. If I have three neighboring hydrogens, so maybe let's say these were chlorine atoms, so there's no other hydrogens here. I've just got this one hydrogen. It's going to be split by all three of these. And each one of these other hydrogens could be aligned with or against the magnetic field in random ways in different moments in time. So only once in a while will all three of them be aligned with the magnetic field, each one increasing the energy of A. So there's only one scenario where that would occur. But that would occur just as often as if they're aligned against the magnetic field, which would decrease the energy absorbed and emitted by A. And so I also see that happening just as often. And then every combination occurs. It's just totally random. So in any given molecule, whether or not each of these hydrogen B's aligned against or with the magnetic field, it's just random. So there's plenty of opportunity for two to be aligned against and one with, or two to be aligned with and one against. And so that's all these scenarios here. So there are three combinations where two are aligned with and one against, and three combinations where one is aligned with and two against. But there's only one combination where they're all aligned with or all against, and so that's why I see this pattern emerge where the two peaks on the outside are smaller and the two peaks on the inside are 3 times bigger, because there's 3 times as many scenarios where that will occur versus the scenario where all 3 neighboring hydrogens align the same way. And so that produces what's called a quartet. And what should the ratios be? The integration of this peak, the area of this peak, would be equal to the area of this peak. And if we set those equal to 1, because there's one scenario in each, giving each of those, then the area of the center peaks would be 3 relative to that, because there are 3 scenarios giving this and 1 scenario giving this. So this all for hydrogen A. And it's due to the fact that I've got multiple molecules. Some molecules, hydrogen A is reacting one way. Other molecules, hydrogen A is affected by hydrogen B differently. And so all of these signals come from hydrogen A, but in some molecules, the signal's a little bit higher in energy, and others it's a little bit lower in energy, depending on, at that moment in time, whether the hydrogen B's line are with or against the external magnetic field. It affects the hydrogen A needs to be absorbed and to excite its nucleus and then re-released, which is detected by the instrument. So if we look at the patterns that emerge here with the scenarios we've already looked at and other scenarios, what we see is a trend where the number of peaks is one more than the number of neighboring hydrogens. Right? So if I have, what we said is, if I have one neighboring hydrogen, that will split that into a doublet. So one neighboring hydrogen produces two peaks, a doublet. If I had two neighboring hydrogens, we saw that gives a triplet. So the number of peaks is always one more than the number of neighboring hydrogens in these simple analyses. We're going to look at exceptions to this in a minute. But generally, as long as all of the neighboring hydrogens are equivalent, so let's say we had a situation like this, where the molecule was symmetrical, maybe we got chlorine here or something. In this situation, hydrogen A is split by 3 hydrogen Bs over here and 3 Bs over there. And due to the symmetry of the structure here, these 3 Bs and these 3 Bs are all equivalent. So now I've got 6 total hydrogens on neighboring carbons that are all splitting hydrogen A. So when there's 6 total hydrogens, 6 neighboring hydrogens, the pattern I see has 7 signals with these ratios. It's called a septet. 7 signals. And so that allows us to come up with a rule, it's called the n+1 rule, where n represents the number of equivalent neighboring hydrogen. Whatever that number is, plug that number in here, add 1, and that tells me how many signals that should be split into. So if there are 3 neighboring carbons, 4 signals gives me a quartet. If there are 5 neighboring hydrogens on the neighboring carbons, 5 plus 1 is 6, so I see a sextet or a 6 signal pattern. So this is a very useful rule, but we really want to emphasize this word here, equivalent. All 6 of these hydrogens that I've labeled of type B have to be equivalent to one another if they're all going to split A in the same way and give the predicted pattern based on the n+1 rule. So a little later we'll see what happens if B's on one side are not equivalent to B's on the other side. So let's look at the n+1 rule a little bit more detail. So 1, we said this already, but this also really needs to be emphasized. If hydrogens are equivalent to one another, they won't split one another. So what we said over here is A is split by B because B and A are not equivalent, right? Clearly A is on the same carbon as the chlorine, B is not. A and B have different environments. So they have to have different environments to split one another. So B is going to split A, this B is going to split A, this B is going to split A. All 6 B's split A, and the signal for A should be split into a 7 peaked signal called a septet. What about the signal for B? Well, if I'm looking at the signal for B, it's on this carbon. The other hydrogens on the same carbon could split it, but they would have to be different spatially. So whenever hydrogens on the same carbon are equivalent, they can't split one another. They can only split one another if they're not equivalent. But A is not equivalent to B, and they're on adjacent carbons, so A could split B. Since there's only one hydrogen there, if I apply the n+1 rule, that's 1 plus 1. 1 hydrogen plus 1 gives me a doublet. So I expect to see a big signal. All the hydrogen B's would give a big doublet that integrates to 6, and hydrogen A would give a septet that integrates to 1, because there's only one hydrogen of that type giving that signal. So what about this molecule here? Well, here there's a symmetry. Right? There is a rotation of this bond where the 2 chlorines and the 4 hydrogens are symmetrically positioned due to a plane of symmetry. So if I can see the plane of symmetry, I know these four hydrogens, or these two hydrogens and these two hydrogens are equivalent. I could also do the replacement test. If I replace any one of these four hydrogens with the deuterium and then rotate the bonds around or flip the molecule over, it looks exactly the same as it would look if I replaced any of the other hydrogens with deuterium. So replacing any one of these gives the same structure as replacing any of the others, which means all four of these are equivalent. So if the hydrogens on the same carbon are equivalent, they can't split one another. If hydrogens on adjacent carbons are equivalent, they also can't split one another. So none of these hydrogens are unique from the other hydrogens, and if they're all equivalent to one another, they all give the same signal when they're not splitting. So all four of these would give one singlet. No splitting when the hydrogens are equivalent. In order to split, hydrogens must be non-equivalent protons, and they have to either be on the same carbon or on the very next carbon. There is one exception to that. If they're two carbons away, it's too far, unless they're on an aromatic ring. So typically a hydrogen, so let's just say we had a chlorine here and maybe an OH here. So I put the chlorine and OH on here so that this ring won't be symmetrical, right? There's no mirror plane here, there's no mirror plane here. I don't really have a mirror plane to make any of these hydrogens equivalent. So in this case, let's call this one A, B, C, and D. So here I would expect to see, just to look at the signal for A, due to it being a different distance from the chlorine and the OH compared to all the other hydrogens here, C, B, C, and D, A is different from the other three. Each one is unique, right? There's no symmetry here. So I would expect to see four signals. And the splitting pattern for A would be pretty complicated, because one carbon away there's a non-equivalent hydrogen to A, which would split it into a doublet. One carbon away over here there's a non-equivalent hydrogen to A, which would be split into a doublet. And normally a hydrogen like hydrogen D that's 3 atoms away from hydrogen A would not split it, and that's what we're talking about down here. Hydrogens that are this far apart don't split unless they're on an aromatic ring. So hydrogen A would be split by C into a doublet, by B into a doublet, and by D into a doublet. And so that might be a very complex splitting pattern that I wouldn't be able to interpret very readily. So it might end up being something called a multiplet, which we'll talk more about in a minute. So if you can't discern the signal's splitting pattern because it's not symmetrical or it's too complicated or maybe it's overlapping with another signal and their splitting patterns are combined into some weird shape, we call that a multiplet. So you want to remember though, hydrogens on the same carbon can split one another, but not if they're equivalent. Hydrogens on adjacent carbons can usually split unless they're equivalent. Hydrogens 3 carbons away won't split if they're equivalent, or even if they're not equivalent, unless they're not equivalent and part of an aromatic ring. Alright, so let's talk about more complex splitting patterns. So we said the n+1 rule applies when the neighboring protons are all equivalent to one another. Right, so if let's say I had a situation like this. Well, let me draw it down here actually. I've got a hydrogen here. I've got hydrogens here. Got 3 here. So maybe I ask you, what's the splitting pattern for this hydrogen? Well, there's no other hydrogens on the same carbon. So it's not obviously going to be split by any hydrogens on that carbon. There are no other ones. Then I want to look 1 carbon away. There's no aromatic ring, so I don't have to look 2 carbons away. I'm just going to look to 1 carbon away. On this side, the carbon has no hydrogens directly attached to it, so there can be no splitting. So these hydrogens here and these hydrogens here are too far away from this hydrogen to cause any splitting. But these three hydrogens are close enough. They're on the very next carbon over. And since these three are all equivalent to one another, n would be equal to 3. There are 3 equivalent hydrogens on the neighboring carbon that are all splitting that. And when I apply the n plus 1 rule, I get 4. So this hydrogen I could confidently predict should give a quartet or a signal that has 2 outside peaks that are smaller, 2 inside peaks that are taller, and then another, and so that would be a quartet. These 3 hydrogens all being equivalent to one another allowed me to use the n plus 1 rule to predict how they're splitting the hydrogen on the adjacent carbon. So let's take...
Really quick.
Yes, go ahead.
Sorry.
Yes, please.
Did you draw a different molecule from the one that's already printed on there? Or is that the same thing?
Oh, this molecule here is different from the one here.
Oh, okay. I was just making sure.
Yeah, so I drew this structure here to illustrate the situation where you can apply the n plus 1 rule for a hydrogen, because the only hydrogens that would be splitting it are all equivalent to one another. So they're all splitting it in the same way with the same coupling constant, and I can predict this pattern using the n plus 1 rule. So let me just contrast that by discussing this one. Hopefully that will be more clear for you. So this hydrogen here, I can't use the n plus 1 rule to reliably predict its splitting pattern. And the reason for that is because there are hydrogens on adjacent carbons that are not equivalent to one another due to the fact that there's no symmetry in the structure. So this hydrogen is too far away from the hydrogens on this carbon or on this carbon. Those are not going to cause any splitting. There's no other hydrogens on the same carbon to split it that would be not equivalent to it. And there's one hydrogen here on this neighboring carbon, and there's one hydrogen here on this neighboring carbon. So this hydrogen, we'll just call these A, B, and C just to be able to communicate about them more clearly. So hydrogen B would be splitting A, and hydrogen C would be splitting A. And so if I were to apply the n plus 1 rule, there's 1, 2 neighboring hydrogens to A that would be splitting it. And so that would be 2 plus 1, and that would give me a triplet. A triplet because 2 plus 1 is 3. Trip. 3. So I would expect to see hydrogen A give me a triplet if I were applying the n plus 1 rule. But I can't reliably apply that rule here, because if hydrogen B is splitting hydrogen A, it might be splitting it with a different coupling constant than the coupling constant C is splitting A with. So let's talk about coupling constants, and then we'll go back and look at that. So a coupling constant is simply a measurement of the distance between the splitted peaks. How far apart are they? And so in this example, A is splitting B. When A splits B, it creates a specific distance between all the peaks, and they're all the same distance apart. If A is splitting B, B has to then be splitting A. So if we're looking at the signal for A, we can apply the n plus 1 rule. A is equivalent to A, so they're not splitting one another, but A is split by B, and there are 3 hydrogens of type B splitting it. And so that's why I see a quartet, 4 signals, and they're all the same distance apart from one another. If I look at B, the signal for B is split by A. So B can't split B because B is equivalent to B. But A can split B, and there are 2 hydrogens of type A. So when I recognize 2 adjacent equivalent hydrogens, both splitting B, I plug that in for N, and I get 3. So that's why I have a triplet here. And the coupling constant here, the distance between these peaks, is the same distance as the distance over here. And so what that means is when hydrogens are splitting one another, they have to do so with the same coupling constant. So let's go back over here and talk about this now. So we have a similar situation here. B is splitting A and C is splitting A. But the coupling constant that B is splitting A with might be quite different from the coupling constant that C is splitting A with, because B and C are not equivalent. So let's imagine HB splits HA with a large coupling constant. So there's no way for you to predict the coupling constant, whether it's large or small. We don't know which one is going to be larger, which one is going to be smaller, but we can predict they're probably not going to be splitting the same. So we'll just say, for the sake of argument, that B is splitting A with a large coupling constant. So that would give me a situation where the doublet that B splits A into would create two peaks that are far apart. Right? The distance between these two peaks is a long distance if I have a large coupling constant. I don't know that B is going to split A with a large coupling constant. But if B splits A with a larger coupling constant than the coupling constant C splits A with, then we're going to end up with this situation. So let's say HC splits HA with a smaller constant, coupling constant. If that happens, then this doublet that's already been created by B splitting A with a large coupling constant is going to be split again. So instead of two peaks, each one is split into another doublet by HC. And since that one splits with a smaller coupling constant, the distance between the peaks that these are split into is going to be shorter. So instead of having one doublet, because B split A, I have a doublet of doublets. I have these two peaks that were split apart by B splitting A, and I still have those with the same distance here, same coupling constant as here. But those were split into another pair of doublets because C is also splitting A with a smaller coupling constant. And so that's the distance between the peaks here is much smaller because C is splitting A with a much smaller coupling constant. And so that's called a doublet of doublets. A triplet is what I would have expected if the coupling constants were the same. And a triplet is really not any different from a doublet of doublets, but it's a doublet of doublets where the coupling constants are equal. So I don't know what the coupling constants are. I don't know if B is splitting A differently from how C is splitting A, or if maybe they're splitting the same. If the coupling constants were the same, though, then this distance between the peaks would be the same as this distance between the peaks. So let's just imagine all of those had small coupling constants. So if they're all equally small coupling constants, then B would split A into a pair of peaks at a certain distance apart. And then C would split that pair into another pair. But with the same coupling constant, the second pair would be... Oh, I didn't draw that well. Let me try that again. The second pair would be overlapping with the first pair because the distance between the peaks in the first pair would be the same as the peaks in the second pair. And so the overlapping part would be in the middle, which would add to that other section that's already in the middle, and that would give me a triplet. So a triplet results from a doublet of doublet that's been positioned at a distance where the inside peak of one doublet and the inside peak of the other doublet overlap to create the center peak of the triplet. So a triplet really technically is a doublet of doublets, but where the two doublets are overlapping a little bit. Right, so when you're looking at a hydrogen, to try to determine its splitting pattern, you got to look at any other non-equivalent hydrogens on the same carbon and you got to look at hydrogens on adjacent carbons. If some of those hydrogens are not equivalent to one another because their environments are different, they might split with different coupling constants. In this case, one would split into a doublet and the other would split into a doublet, so I might get a doublet of doublets. But if they split with the same coupling constant, I might also see a triplet. So let's look at a couple other examples to hopefully try to illustrate that point. All right, so let's look at these splitting patterns here. So I've got some hydrogens. I'm going to draw them in first. Got one here, got one here, and then we've got a bunch of on here and on here. So first thing we want to do is to determine which hydrogens are equivalent and how many signals there are, because we know equivalent hydrogens cannot split one another. So these three hydrogens are all equivalent because they're all on the same carbon. We said any methyl group will be equivalent. Because I can rotate this bond freely, these hydrogens here will have the same environment as the three down there. They could easily swap positions and rotate around. This hydrogen is obviously unique. It's the only one of this type with the environment it has around it. These two hydrogens over here are equivalent to one another. There's no chiral center. And so because this molecule is basically flat, the one on top and the one on the bottom have equivalent environments. So I could call these both C. And then looking at the ones attached to the double bonds, I see they're all also unique because there's no symmetry in the structure. I don't have a plane of symmetry here or here, really anywhere. And so this one would be unique, and this one would be unique, and this one would be unique. It might look like E and F are the same, but because F is closer to this isopropyl group in space, and E is farther away or on the other side of the ring, they're not equivalent spatially. So I've got a number of signals here. I want to predict their splitting pattern. So what's the splitting pattern for A? Well, A can't split A because they're equivalent. So A can't be split by any other hydrogens on the same carbon, but on the next carbon over, there's a hydrogen. There's only one. So that's N. So N plus 1 is going to be 1 plus 1, which equals 2, which gives me a doublet. The signal for all 6 hydrogens A will all be doublets, and they'll all be in the same spot, stacked on top of one another, giving an integration of 6, because there are 6 hydrogens of the type HA. Looking at HB, HB isn't split by any other hydrogens on the same carbon. There are no others. It's not split by anything here. There's no hydrogen there. But it is split by these 3 and these 3. So B is split by 6 total hydrogens on adjacent carbons. But because all 6 of those are equivalent, every one of these HA is going to be splitting HB with the same coupling constant. So since they're all splitting with the same coupling constant, I can use the N plus 1 rule. And since there are 6 of them, that gives me a septet. 7 signal pattern for HB. Alright, let's look at HC. What's happening with HC? HC is split by, it can't be split by another HC, they're equivalent. There's nothing over here to split it. It's only split by D. And so that one hydrogen would be giving me a doublet. HD is split by C, but there are 2 equivalent hydrogens there. So in this case, N equals 2, and I would expect to see a triplet for that signal. For E, there's nothing splitting from this side, but it is split by F. Since E and F are not equivalent, they'll each be splitting each other. And so since there's one type of F splitting E, that splits E into a doublet, and there's one type of E splitting F, so that splits F into doublet. So I didn't have any complex splitting patterns here, because each hydrogen that's being split by neighbors, all of its neighbors are equivalent, so they're all splitting with the same coupling constant. We did say that when hydrogens split one another, they'll do so with the same coupling constant. So in this case, I call these A and these B. If hydrogens A are splitting B into a triplet with a certain distance between the peaks, this is a very small coupling constant, the peaks are very close together, B has to be splitting A with the same coupling constant. So that's why we see the peak distance here is the same small coupling constant distance between the peaks as we have over here between the peaks. And this is a common pattern. There are a lot of times where it might have an ethyl group, maybe attached to an oxygen, where these two split these three into a triplet, and these three hydrogens split those two into a quartet. So seeing a combination of a triplet and a quartet where they have the same coupling constant is a nice way to try to recognize that my structure has an ethyl group in it. I do have to recognize, though, that they have to have the same coupling constant if they're both splitting one another. So if I see a triplet over here that has a small distance between the peaks, a small coupling constant, and a quartet somewhere else that has a larger, clearly larger distance between the peaks, a larger coupling constant than that one, that means they're not splitting one another. This quartet results from being split by some other hydrogen in the structure, and this triplets resulting from some splitting somewhere, but they're not splitting one another, so they're not on adjacent. They're not adjacent carbons. Otherwise, they would have to split with the same coupling constant, and the distance between the peaks would be the same for both of them. So the coupling constant is not something we spend a lot of time talking about the exact value for the coupling constants, but they are relevant to looking at whether hydrogens are splitting one another. Because if one is splitting one, it has to be splitting back. They have to be splitting each other if they're splitting at all. And if they are splitting each other, they have to do so with the same coupling constant. So some other common patterns that you might look out for recognizing. A terp-butyl group. If I have a terp-butyl group, maybe it's bonded to an oxygen, or maybe it's bonded to a carbon. It doesn't matter. If these three hydrogens, these three and these three, are all equivalent due to some rotation here, free rotation, and there's no hydrogens on the neighboring carbon to split them, they shouldn't give any splitting. And that's why I just see a singlet. And it should integrate to 9 relative to other peaks because there are 9 total hydrogens all giving the same singlet. So if you see a big singlet that integrates to 9, that's usually indicating a terp-butyl group. If I have an iso group, like an isopropyl, then in my isopropyl, let's say there are no hydrogens on this carbon. So let's just say maybe there's an oxygen here or something like that. That would mean that this hydrogen isn't split by anything over on this side, obviously, but it would be split by 1, 2, 3, 4, 5, 6 equivalent neighboring hydrogens, and so 6 plus 1 is 7, and so that's why I see 1, 2, 3, 4, 5, 6, 7 pattern signal called a septet right here, and that would integrate to 1 because it represents a signal from 1 hydrogen. Its integration would be 1 in relation to the integration of this doublet that has the same distance between the peaks and the same coupling constant because they're splitting one another. So these 6 hydrogens are only split by 1. It's splitting them into a doublet, and that's why I see the slight distance between those peaks giving me a doublet with the same coupling constant that the septet had. And so that means they're splitting one another. As we said, if they're splitting one another, they have to do so with the same coupling constant. So an isopropyl group will give you 2 signals for the 2 different types of hydrogens. One will be split a lot by the other 6, and one will be split only once by the other 1, and their integrations will be a ratio of 1 to 6. So that's a lot of data confirming the isopropyl situation there. All right, let's look at a couple more examples of complex splitting patterns. So we talked about this idea. Let's look at some more examples. So here we're looking at the signal for HB. I expect HB to not necessarily follow the n+1 rule because it's being split by hydrogens of different types. There's no symmetry here, right? X could be some other grouping, but there's an X over here, and here there's a hydrogen. So I don't have a symmetry. The molecule's not symmetrical. It creates a situation where HA has a different environment from HC. So when I have two different types of hydrogens in HA and HC that are both splitting HB, they may or may not split with the same coupling constant. So we have a couple different scenarios that we might observe. We can say if HA and HC both split HB with the same coupling constant, then we can use the n+1 rule. So we would have 1, 2, 3, 4, 5 neighboring hydrogens, and so 5 plus 1 would give me 6, and I would see a sextet. I might see that, but I might not. It depends on what the coupling constants are. So what are some other scenarios? So if A is splitting B and C is splitting B, and both those are happening with the same coupling constant, I would expect to see a sextet. Well, what if the coupling constants are different? So what if the coupling constant, which is represented by the symbol JAB, this J stands for coupling constant, I'm not sure why they went with that, but the coupling constant between A and B is very large compared to the coupling constant between C and B. Well, A is splitting B into a quartet because there are 1, 2, 3. 3 plus 1 is 4. And so A would be splitting B into a quartet. And that's what I see. 1, 2, 3, 4 signals that are separated by a larger distance because of the greater coupling constant. But C is also splitting B. So instead of seeing a quartet that looks like this, each of the individual peaks of the quartet is split further by C also splitting B. And so if C happens to be splitting B with a much smaller coupling constant, then the distance between the peaks it's splitting these individual peaks into is not going to be very great distance. And so with C, there are 2 hydrogens of that type. And so 2 plus 1 gives me a triplet. And that's why I see triplets for each one of those. So what is this? It's a quartet of triplets. I've got 4 triplets, a quartet of them. And that's what I see if the quartet has the larger coupling constant and the triplets have the smaller coupling constant. But I don't know if that's the case. I don't necessarily know what the coupling constants are. So it's possible that the coupling constant between B and C might be large compared to the coupling constant between A and B. So we have another scenario. So there are really 4 possible scenarios here. One where the coupling constants are equal, giving me a more simple pattern predicted by the n+1 rule. One where the coupling constant between A and B is larger than between B and C. One where the coupling constant between B and C is larger than between A and B. So if C is splitting A with a large coupling constant, there are 2 hydrogens of type C, so that's 2 plus 1, that's a triplet. So that's why I get a triplet. 3 groupings of atoms at a larger distance because I have a larger coupling constant with which C is splitting A into triplets. If A is splitting B with a smaller coupling constant, then I get a smaller distance between the peaks of my quartets. So A, there are 3 hydrogens of that type, 3 plus 1 equals a quartet. So that's why I have 3 small quartets. It's a triplet of quartets. It's a triplet, and each peak of the triplet is split into a quartet, so it's a triplet of quartets. One grouping of hydrogens with the larger coupling constant is splitting it into a triplet, and the other group is splitting those triplets into quartets with smaller coupling constants. So I see a triplet of quartets, I see a quartet of triplets. I don't know which I'm going to see unless I know what the coupling constants are. And the fourth possibility is, what if the coupling constants are similar but not exactly the same? Then I might get something that kind of looks like the sextet we expected to see if the coupling constants were exactly the same and we apply the n+1 rule. But it's not going to be necessarily symmetrically detectable what the pattern is. So if the pattern looks non-symmetrical, we could just call that a multiplet. And we would need a higher magnetic field in our instrument to be able to separate that out. So the more powerful the magnet is, the greater the distance between the peaks on the graph. And that would allow me to get a better distance between these and see if I have a quartet of triplets or a triplet of quartets if I use a more powerful magnet. Any questions about any of that? All right, so looking back at this example, let's see if we can predict all the splitting patterns here. So, real quick, these three hydrogens are equivalent. We'll call those A. We'll call this one B. This one will be C. It's unique, obviously. There's no other hydrogen on an oxygen. This will be D, E, and F. So what should the splitting pattern be for hydrogen A? Well, they can't split one another, but there is one hydrogen on the neighboring carbon, so that one hydrogen, 1 plus 1, should split A into a doublet. Let's look at B. What is B split by? B is split by A, and it's split by D. But A and D are not equivalent. So I can't just add those up and say that there are 4 neighboring hydrogens, and that those hydrogens are splitting B into a 4 plus 1 quintet, because they're probably not splitting with the same coupling constant. So maybe it'll be a quintet. If they were splitting with the same coupling constant, maybe it'll be a multiplet. If they're splitting with similar but not quite equivalent coupling constants. Or maybe if A splits B with a large coupling constant and D splits B with a small coupling constant, then I would have a quartet of doublets. A would be splitting B into a quartet, D would be splitting B into a doublet. So a quartet of doublets, or a doublet of quartets. So it really depends on which side is splitting with a higher coupling constant and how much of a difference there is between those coupling constants. What about HC? Well, what we're going to see a little later is usually a hydrogen on a highly electronegative atom won't get involved in splitting. So that could be a singlet. And that's because the hydrogen might be constantly exchanged with the solvent because the OH bond can break. This could be slightly acidic or basic. The oxygen could pick up a different proton and then drop this one off somewhere else, or could drop this proton off and take on a negative charge and then pick another one up. So since the hydrogens are constantly being exchanged between molecules, they don't spend enough time on any one molecule to get involved in splitting usually. So I usually see a singlet. But I might see a doublet if the sample does not undergo fast exchange for that hydrogen exchanging with other hydrogens. It might actually get involved in splitting, and if it were, it would be split by B and do a doublet. So there's a couple possibilities for that as well. HD, we talked about that. HD would be split by B and by E. So if they had the same coupling constant, it might be a triplet or probably a doublet of doublets if they were splitting with different coupling constants. HE, so you can start to see these splitting patterns can get pretty crazy, especially if they're overlapping with one another, because E and D are both on sp2 hybridized carbons. They might have really similar shifts. they both be probably between 4 and 6. And if they start to overlap, then one doublet of doublets overlapping with whatever pattern this is going to give, it could make the pattern even more complicated, in which case I would just call that a multiplet. But E is going to be split by D into a doublet. E is going to be split by F into a quartet. So the situation for E is very similar for the situation for B in terms of splitting. I've got 4 neighboring hydrogens. If they all split with the same coupling constant, 4 plus 1 would give me a quintet. If they split with similar coupling constants but not exactly the same, I might get a multiplet. Or if the quartet splits it with a bigger coupling constant than the doublet, I get a quartet of doublets. If the doublet splits with the bigger coupling constant than the quartet, I get a doublet of quartets. And then, so finally, HF, they can't split one another, they're equivalent. They would be split by E, and there's only one hydrogen of that type, and so it would split them into a doublet. As we said, hydrogens on an oxygen or on a nitrogen could potentially be exchanged with the solvent. And so we don't always see them splitting. So here's the NMR that you might see for ethanol. So I've got 3 hydrogens of this type and 2 of this type. So these 3 are splitting this 2 into a quartet. These 2 plus 1 is 3, are splitting that into a triplet. So we'll just label these A, B, and C. So A is here being split by 2 into a triplet. B is here being split by 3 into a quartet. Why is B so much further downfield than A? Because it's much closer to the electronegative atom. And C would be here. So normally I would expect a hydrogen to be split by the hydrogens on the adjacent carbon. So these 2 would split C into a triplet. And I might see that. But I also might see it as a singlet if the splitting isn't occurring. So the OH proton is not being split. That means it's being exchanged with the solvent or with other molecules. And so swapping hydrogens back and forth can happen. If that happens at a faster time scale than the NMR experiment, the hydrogens won't be on any given oxygen long enough to engage in splitting, and that's why I see a singlet there. And that's what this is basically saying. If a proton is on an oxygen or some other atom where it's labile, meaning that it's easily to remove or replace, that means it's exchangeable. And the rapid exchange, especially if there's tiny trace amounts of acid or base catalyst present, that can mean that the hydrogens don't stick around long enough to get involved in splitting. And so that shielding, deshielding effect that causes the splitting isn't present. So let's just talk about how that would happen really quick in terms of the mechanism. So if one ethanol molecule were to react with another, it could pick up that proton. So that would produce 2 formal charges, which would be pretty unstable. So it doesn't happen too often. So let's call this one A and this one B. And then there wouldn't be much of this around solution at all because it's relatively unstable with formal charges. But B, the hydroxide here, the OH minus, could then pick up proton A, which would give me the same structures, but now HB is on the first structure where A was, and HA is on the second structure where B was. So swapping back and forth through this proton transfer steps makes it so A and B aren't really on any one oxygen long enough to be split by the protons on the neighboring carbon. If you rigorously remove traces of acid that speed this process up, so if I had an acid, like some H3O plus or something like that, this oxygen probably pick up a proton from the acid first. And then a water or another ethanol could pick off HA. So these protons getting swapped back and forth is sped up by starting with something that's unstable, because if I looked at the reaction accord diagram, the H3O plus is relatively high in energy to begin with, so that lowers the activation necessary to do the proton transfer step. It happens a lot more often with that around. Without it around, the process that we showed here initially, where the two ethanols produce two formal charges, that happens pretty rarely. So that would be slower. So if I remove all traces of acid, then I might actually see the splitting because the rate at which the protons are transferred back and forth goes way down, and each individual proton stays on the oxygen longer, so it can actually split with the protons on the neighboring carbon. And then one other thing you want to be aware of is that aldehyde protons, aldehyde looks like this. So if the R group is actually some chain or something, well then there would be hydrogens here. And the aldehyde proton, which is this one, is, you would imagine, going to be split by these neighboring protons. And if you have a really high-powered magnet or look really closely, you probably would see the signal for that proton as a tiny doublet. But when the two peaks are very close, because the coupling constant is super, super small, it might look like a singlet. So you got to be a little bit careful about protons that are part of an aldehyde functional group. Even if there are adjacent protons, you might not see splitting because the coupling constant would be too small for you to discern the two peaks as being different. Sometimes you'll see a peak entirely disappear. And that occurs if there's a deuterated solvent that is exchanging deuterium for protons. So any of these protons that are exchangeable because the oxygen or the nitrogen could pick up a different proton and then lose that one and replace it with a new one. If the solvent is something that has a deuterium atom, then the proton might get exchanged for deuterium. So any one of these could use a lone pair to pick up this deuterium. Now, normally we don't see carbon with a negative charge. But in this case, the chlorines through induction are attracting a lot of electrons away from that carbon, so that really helps to stabilize that extra negative charge. And then the nitrogen would now have both a deuterium and a proton attached. It would have a positive charge. So this carbon is probably pretty unstable with the negative, so it would just pick up that proton. And so that would mean that the nitrogen now has a deuterium attached, and the chloroform has a hydrogen attached. So if the solvent is deuterated and the deuterium of the solvent is exchangeable, and I've got maybe a lot more molecules of solvent around than I have the other molecules I'm trying to analyze, that equilibrium, because I have so much reactant as the solvent, would be shift toward the product side. And so instead of seeing a signal for the hydrogen that was bonded to the nitrogen, if it's exchanged with the deuterium, I wouldn't see that signal anymore at all. And so that's something that we could explore here. If ethanol were added to an exchangeable deuterated solvent like D2O, which is just water where the deuteriums replace the hydrogens, exchanging that hydrogen for a deuterium could convert the ethanol into deuterated ethanol. And now instead of having a hydrogen here or a deuterium, this peak would be gone. Right? I only see that peak for the hydrogen if it's a proton. Deuterium's not detected in proton NMR. So if you're looking for a signal for a hydrogen that's bonded to a highly electronegative atom, if you're using a deuterated solvent, that signal might not be there. So that's another key detail that you want to be aware of. All right. So let's look at another example. The best way to really practice is to look at as many examples as possible. So here, if I'm looking at the proton NMR, I want to draw in the protons. Got one here, 3 here, and 2 here. So then we want to label them, make sure we understand how many signals there would be. These 3 would all be equivalent due to rotational symmetry around this single bond. Would these 2 be equivalent? No. 1, because this double bond can't rotate, is on the same side as this group, and the other is on the same side as this group. So these would definitely be unique. So I got A, B, C. This one's unique, D. These 2 are equivalent. There's no chiral center to make them spatially different. They're different from these 2 because these 2 are adjacent to 2 CO double bonds, and this one's only adjacent to 1. So that should give me 6 signals. So for HA, what do I expect to see? I expect to see an integration of 3 relative to the other integrations because there are 3 hydrogens giving this signal. I expect the position to be around 1 ppm for a proton that's on a methyl group, but it's also allylic, so that's probably going to add another 1. So it's going to be around 2 ppm, roughly. And what's the splitting pattern? Well, there's no hydrogen on the adjacent carbon to split it, so D a singlet. HB. HB would give an integration of 1 relative to HA because there's only 1 hydrogen given that signal compared to 3 for the other signal. What would its shift be? Well, it's on an sp2 hybridized carbon. If it's on an alkene, I expect it to be between 4 and 6 ppm. If it were on an aromatic ring, which is also like an alkene, that I would expect to see between 6 and 9 ppm. So there's a slight difference between whether it's on a standard double bond or whether it's part of a ring of alternating double and single bonds. That's what I expect for B. Is B going to have a splitting pattern? Well, there's no hydrogens on the neighboring carbon here to split it, but since it's not equivalent to C, they would end up splitting one another, even though they're on the same carbon, because they're spatially non-equivalent, they don't have the same environment, they should be splitting one another. So I'd expect B to be a doublet, and C, which would appear somewhere close by because they're both on the alkene, they would both be doublets because they're splitting one another, and they would have the same coupling constant. All right, let's take a look at hydrogen D. What's happening with D? Hydrogen D, again, 1 hydrogen of that type giving the signal. Where would its shift be? Well, it's on a methine, so it's usually going to start around 1.7. It's adjacent to a CO double bond, so that's going to add 1. It's also allylic to this pi bond, so that should probably add about 1. So I expect that to be around 3.5 to 4 most likely. And what's its splitting pattern going to be? There's nothing here to split it, there's nothing here to split it, but it's going to be split by 2 equivalent hydrogens on this side. So 2 plus 1 would give me a triplet. Looking at E, there's 2 hydrogens of that type, so that peak should have twice the area of the peaks that had 1 hydrogen producing their signals. And the shift for E, it's on a methylene, CH2, which normally starts around 1.2. And what am I adding here? There's nothing really over here electronegative to change it, but it is 1 away from this CO double bond, so I'd add 1 to that. So that's probably going to be somewhere between 2 and 3 ppm. And those hydrogens would be split by 1 adjacent hydrogen, so there's nothing up here to split it. There's 1 hydrogen here to split that into a doublet. And finally, HF. HF represents 2 hydrogens, so the integration should be about 2 with respect to the other integrations. its shift, it's a methylene, it's adjacent to one CO double bond, and it's adjacent to another CO double bond on the other side. So that's going to give me a shift of around 3 to 4 ppm. And that one doesn't have any neighboring hydrogens on adjacent carbons or on the same carbon to split it, so it should be a singlet. So here is the molecule that you were to analyze for the quiz. So let's take a look at this one. Draw it bigger so we can draw in the hydrogens. So here, how many different signals should we get? Well, these three are all equivalent due to the rotational symmetry there. So these would all be maybe A. There's definitely a hydrogen here to make 4 bonds for that carbon. We'll call that B. I've got 2 here and 2 here. So here I have to recognize that there is some symmetry here. Because this bond can rotate, it's not correct to think of the methyl group only being on one side. If it couldn't rotate and it were only on one side, it would make the hydrogens on this side different environments than the one on the other side, and they wouldn't be equivalent. But because of the free rotation here, the methyl group is going to be moving around like a propeller, on average, affecting both sides of this ring the same way. So these 2 hydrogens on this side are equivalent to the ones on the other side. So we can call all 4 of those hydrogens C. And for the same reason, the same symmetry means that these 2 are equivalent as well. So I've got 5 signals there. So I'm going to do the same thing we did in the last problem. Try to predict their integration. So there's 3 hydrogens of this type. So the integration would be 3 relative to the signal for HB, which would have an integration of 1. And again, when we talk about integration, I don't know that it's not like the area is going to necessarily equal 3. It's just going to equal 3 times the area of the signal for hydrogen B. So I'd have to usually set the smallest signal to 1 and see where the other ones come up and see if they come up to ratios that make sense for whole numbers of hydrogens. But HA, in terms of its shift, it's a methyl, so it's going to be around 1 ppm. But it is directly connected to an oxygen, which we said should add about 2.5 to 3 to it. So I expect that one to be somewhere between 3.5 and 4 most likely. And it should be a singlet due to there not being any hydrogens on the very next carbon to split those 3 equivalent hydrogens. Hydrogen B represents 1 hydrogen. Where will its shift be? Well, it's on a methine, which starts around 1.7. And it's directly connected to an oxygen, not the hydrogen itself, but the carbon it's on. So that adds about another 2.5, and so it's going to give me about 4 to 4.5 ppm, most likely. And the splitting pattern for that one is going to be affected by the neighboring hydrogen splitting it. So there are 1, 2, 3, 4 hydrogens of type C that are all splitting B, because they're all adjacent to it. And so for B, that's going to be 4 plus 1, giving a quintet for its splitting pattern. That's what I expect to see. If these hydrogens on this side were not equivalent to these, they might split with different coupling constants, and I might see a more complex pattern. But in this case, all 4 H of HC are equivalent, and so 4 plus 1 gives me a quintet for B. Looking at the splitting pattern for looking at the analysis for HC, there are 4 hydrogens of that type, so its integration or area of its peak would be 4 times greater than that for hydrogen B. The shift there, I would start with a 1.2 for the methylenes, a CH2. And it's too far away from this oxygen to be much affected, but it is allylic to the pi bond here, so that's probably going to add about 1. So that's going to give me around 2.5 somewhere for the ppm of that. And HC, that's where the splitting pattern is not going to be totally discernible. Because for HC, it's 1 away from D, which is going to split it, and it's 1 away from B, which is going to split it. And I would do the same analysis if I looked at the other side. So B is going to be splitting C into a doublet, and D is going to be splitting C into a doublet. If they do so with the same coupling constant, then the two doublets are to overlap. I would add together and produce a triplet. So I might see a triplet, or if they split with very different coupling constants, one would give me a very small coupling constant, but the other would give me a very large coupling constant, so I would see a doublet of doublets. Or if they did start to overlap but didn't overlap symmetrically, I might see something that wasn't quite a symmetrically shaped signal, which I would label as a multiplet. So I can't say for sure which of those three I will end up with unless I know the coupling constants or actually do the experiment. So then for HD, there are two hydrogens of that type, so its integration would be twice the integration of HB, or half the integration of HC. These are directly connected to an alkene, so they should be between 4 and 6 ppm. So if it's directly connected to a double bond, I'm not starting with a CH or a CH2 or a CH3. I'm not using the method we talked about last time where I start with how many hydrogens are on the carbon and then start adding things. I just know if it's on a double bond, it's going to be between 4 and 6, and there's information about that to help you on your formula sheet, so you have to memorize it. Then, in terms of splitting pattern, this D is split by C, and this D is split by C, and they're splitting the same way because it's symmetrical. So the two hydrogens of type C are splitting D, and so it's going to be 2 plus 1 equals a triplet. So this D will give a triplet, and this D will give a triplet, and they'll be equivalent. There'll be two triplets right on top of one another, and that's why the integration will be twice the integration for HB. Questions about that one? Okay, a couple other things to look for. You want to be aware of how symmetry works on aromatic rings. So if I have two equivalent groups attached to this ring, it means I've got some symmetry here. Right? Reflectionally or rotationally, these two hydrogens are equivalent to these three. So they will give one signal that has an integration of 3 times the signal for the integration of the blue or yellow hydrogen. This signal here, so these I could label these A, these B, and these C. So I would get 3 total signals with this type of symmetry. And that would be pretty different in the NMR versus these other two, because over here, when I have these methyl groups 3 carbons away instead of on adjacent carbons, there's still some symmetry, because rotationally or mirror plane symmetry there, these would be equivalent, these would be equivalent. But I don't have any symmetry here, because up here this one's sandwiched between two CH3s and this one's not. So here I would get a total of 4 signals in the proton NMR. Now those signals might be similar, and so they might overlap and it might start to look like a big multiplet, but if I had a really nice, powerful NMR machine, I could separate those out and see their individual signals. Looking at the structure here, when I have 2 identical groups on opposite sides of the ring, now I have more symmetry. Oops. The right hand side is equivalent to the left, the top is equivalent to the bottom, and so in this case, if I tried to do the replacement test, replacing any one of these hydrogens with the deuterium, I could rotate the molecule around or flip it over, and it would look exactly the same as it would look if I replaced any of the other hydrogens that are blue with deuterium. So I would see 1 signal in the aromatic region between 6 and 9. And I would see one signal, obviously, for these 6 hydrogens down around closer to 2 ppm. So these 3 molecules would be pretty difficult to distinguish by IR or mass spec. By IR, they would give CH stretches a little bit above 3000 because it's an sp2 hybridized carbon. They would give CH stretches a little below 3000 because of the sp3 hybridized carbon. But that's true for all 3 structures. How can I distinguish between them? I can't by IR. And in the mass spec, they would probably have pretty similar polarities. So they might travel through the GC at very similar rates. The GC probably would be able to separate them because that tube is really long inside that instrument. It's all wound up and there's a super long tube. So eventually over time, one would probably come through the tube faster than the other due to having a slightly different boiling point. So that I might be able to distinguish between them with mass spec using the GC. But the mass spec would be very similar. They're all the same mass. They have the same molecular ion peak. They have the same number of carbons, so they have the same M+1 peak. And since they all consist of methyl groups attached to a ring, it's likely that once an electron is knocked out, they would probably lose a methyl group or 2. And so the fragments would probably be pretty similar as well. So it would be difficult to definitively distinguish between them through mass spec. But the number of signals they produce in the proton NMR would be different. And I would be able to distinguish between them that way. So that's illustrating, hopefully, to you the power of NMR and why it's often the go-to technique. It gives you the most definitive answer often about what structures you have on hand. And so here's another example to illustrate that. So these 2 structures would be almost identical by both IR and mass spec. In the IR, they would each give signals just below 3000 for the CHs on sp3 hybridized carbon. They would each give signals a little above 3000 for the CHs on sp2 hybridized carbons. I have that in both structures. And in the mass spec, they're isomers. They're constitutional isomers, but in this case, the difference between their constitutions is pretty minimal. They both have one methyl group on this chain and a couple double bonds. It'd be difficult to tell the difference between their fragmentation patterns. But I can see a difference in the NMR here. And what do I see? Well, there'd be a clear difference in the splitting pattern. So we'll just point out, there'll be a lot of differences actually in the NMR, but we'll just point out some of the most glaring ones. So in this structure here, what I'm noticing right off the bat is, since there are no hydrogens on this carbon, this CH2 would be splitting this CH3 and vice versa. So the CH2 would split the CH3 into a triplet. The CH3 would split the CH2 into a quartet. So I would see a triplet quartet. And the triplet and the quartet would have the same coupling constants. I don't have that over here. I don't have an isolated CH2-CH3 group that would cause a triplet quartet to form with the same coupling constant. What else am I seeing here? 1, 2, 3, 4. Yeah, so that would probably be the biggest difference. There would obviously be some other differences. A lot of these splitting patterns would be pretty complicated because the hydrogens are being split by multiple different types of hydrogens. Yeah, that would be the main difference. Looking for that triplet quartet would be the first thing I would look for to tell me for sure which of these molecules I actually had that I was working with in the NMR. Alright, so let's say I give you a formula and I ask you to try to determine the structure of the molecule. So this is adding on to what we talked about last time. One thing you want to do is to determine the degrees of unsaturation. What does that tell you? It tells you whether or not the structure has any double bonds or triple bonds or rings. Right, so if we know the formula, we can figure out from the formula whether or not there are any degrees of unsaturation. And remember, one double bond or one ring is 1 degree of unsaturation, and a triple bond is 2 degrees of unsaturation. Then we're going to look at the NMR, look at the signals, and try to put together some fragments. And then we'll try to connect those fragments to assemble a structure, sort of like a puzzle, that matches the NMR. It's actually very much like a puzzle. So let's look at an example where we can do that. So here's my formula, C7H13Cl. So the first thing I would do, calculate the degrees of unsaturation, and the textbook gives a complicated formula for that. You're welcome to use that formula. I believe it's on the formula sheet, but I would just probably do that through a little bit of trial and error. It's probably easier and faster. So I would put together 1, 2, 3, 4, 5, 6, 7 carbons. This is the formula calls for. And add a chlorine. I would just add it anywhere. And then I would count how many hydrogens that structure would need to be saturated. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if I had 15 hydrogens, it'd be saturated, which means I wouldn't have any double bonds or rings. But if I have 13, that's 1 degree of unsaturation. So that means my structure has to have some kind of ring or some kind of double bond somewhere. I also know it has only one ring or only one double bond. It doesn't have multiple rings or multiple double bonds. It doesn't have a triple bond, because if it had multiple degrees of unsaturation, there'd be less than 13 hydrogens. There'd be only 11 or 9. So I know my structure has to have 1 degree of unsaturation. Is it likely to be a ring, or is it likely to be a double bond? Well, there I can look to the NMR. Right? So what we've been saying about these NMR signals is signals that usually come between 4 and 6 ppm. Those are usually hydrogens that are bonded to an alkene. So the fact that I've got signals right in the area where I expect to see for hydrogens attached directly to a double bond or vinyl hydrogens suggests that my 1 degree of unsaturation probably is going to take the form of a pi bond. So I know my structure is going to have a pi bond. Now I want to look at these NMR signals. What are they telling me? And so the next couple steps involve analyzing the signals and trying to draw fragments that we can piece together like a puzzle. So what I'm seeing here is this hydrogen signal is indicating a hydrogen that's on a double bond. The double bond has up to 4 possible hydrogens, or really 3 if it's going to be connected to the rest of the structure. But what I see here is the integration is 1. But I also have another signal that indicates a hydrogen on the double bond that also has an integration of 1. So that tells me in my structure, somehow I'm only going to have 2 hydrogens on the double bond. Because if I had a third one, that one would also come between 4 and 6, and that would add to the integration or give me another signal. I've only got 2 signals that come between 4 and 6, and a total integration between the two of them of 2 hydrogens. So I can only have 2 hydrogens attached to my double bond. So I'm starting to put some fragments together for what the structure might look like. So let's look at some of these other peaks. At 3.4, I've got a singlet that integrates to 2. So somehow I've got 2 hydrogens probably on the same carbon if they're equivalent. But if it's a singlet, that means on the neighboring carbons there are no hydrogens. Otherwise they'd be splitting those 2 into something more than a singlet. So that gives me kind of another piece of the puzzle. Right, so each NMR signal gives you a little bit of a piece of a puzzle. What I'm also seeing here is the shift here is around 3.4. Normally a CH2 comes around 1.2. So what could possibly shift that up 2 more ppm units to around 3.4? Well, maybe the chlorine is nearby. That's a highly electronegative atom. The formula tells me that that's in there. So maybe I want to think about a chlorine being here. That would also help me to recognize that, at least on that side, nothing's going to be splitting these hydrogens. And so that helps to explain why they'd be a singlet and why they'd have the shift that they do due to the highly electronegative chlorine nearby. So that helps me to put more detail into that fragment that I'm going to try to use to piece together this structure. Looking at the next signal around 2, that's a doublet that integrates to 3. So how do I get a doublet that integrates to 3? Well, if it integrates to 3, that is usually a methyl group. And if it's a doublet, it means that on the neighboring carbon there's only one hydrogen. So the other things attached there cannot be hydrogens. Right, that one hydrogen would split these three into a doublet. Why would that shift to around 2? Typically a methyl group shifts to around 1. An extra ppm unit could come from it being allylic. So if I'm thinking about those 3 hydrogens integrating to 3, being split by one neighboring hydrogen, and shifted to around 2, it's probably because that's where the double bond is. So I'm starting to see how this piece now connects to that piece. And finally, this signal here gives me a lot of information. It tells me I have 6 equivalent hydrogens that are a singlet. And their shift is around 1. So that means they're not close to the chlorine or the pi bond. And so what that would look like would be 6 hydrogens that are all equivalent. And on the carbon that they're connected to, there can't be any hydrogens there. If there were a hydrogen here, you'd be splitting those into a doublet, but I don't see a doublet, I see a singlet. So there can't be any hydrogens there. So I've got 2 methyl groups attached to the same carbon, producing 6 equivalent hydrogens. And so now I got to kind of piece these puzzle pieces together. So since this looks like it kind of is the end piece, like when you put together a puzzle, you put in the corners first and you work on the end pieces first because they have they're on the end because they can't have anything else attached to them. So I kind of see that here, right? Nothing else could be attached to these hydrogens, and something can be attached here, but nothing else anywhere else. So this is like an end piece for my structure. So maybe I'll start there. And this is a skill that takes a lot of practice, so you definitely should be practicing these ones in the textbook if you want to get questions like this on the exam correctly. So I'm going to connect this to something. So I want to recognize that maybe it's connected to this piece. So it's some trial and error. I could try to connect it to the other pieces and see what happens. But if I connect it to this piece, that will help make sure that there are no hydrogens here to split these, because I know these came through as a singlet. So I would connect that piece right there, right, the 2 methyl groups right here. That would give me this hydrogen here. Oops. And that matches what we said we expected to see in this piece. So we put the first piece connected to the second piece, connected to the third piece, and then lastly we had this other piece. So we'll just connect that here. See how the structure looks. So I want to make sure it matches my formula. I've got 1, 2, 3, 4, 5, 6, 7 carbons, 1 chlorine, and counting up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. So it matches the formula. And since all the pieces match the pieces, it should match the NMR, but we want to double check that. So this proton is giving a doublet of quartets. Do I have a proton that would give a doublet of quartets? Yes, this one here. So we'll call this one A. This one would give a doublet of quartets probably because it's split by these 3 into a quartet and by this one into a doublet. Looking at the second peak, that should be a doublet. And that also has to be connected to a pi bond, and that would be this one here. HB matches really nicely with the data. It would be a doublet because there's nothing here to split it. It would be split by this one into a doublet. it has an integration of 1, and it's right in the area we would expect a hydrogen to be that's bonded to a double bond. The next signal, the 2 hydrogens that gave a singlet, right here. Yeah, we put that piece together. We recognize those 2 must be on a carbon next to a chlorine. That's why they shifted down around 3 instead of around 1. They're a singlet because there's no hydrogens on the neighboring carbon or chlorine to split them. And the integration is 2, matching with the number of hydrogens we have there. And the next signal, so let's call those hydrogen C. We want to account for everything, right? So when you have an NMR, and this is what I'll be looking for your Lab 7, in the NMR spectra that you got for Lab 7, you should be able to label each peak or signal and label each hydrogen in the structure so that you can communicate which hydrogen in the structure produces what peak. Every hydrogen should be assigned to a certain peak. That's how you know that the structure matches the NMRs. That's what we're doing here. So we've assigned this signal here as hydrogen A. It matches up. This signal here matches up with hydrogen B. This signal here matches up with the 2 hydrogens of type C. The next signal is giving an integration of 3. And that's this one down here. We expected it to be a doublet. It should shift around 2 because it's allylic. And so that would be D. Right? Those 3 hydrogens integrate to 3, and they're split by hydrogen A into a doublet, and since it's allylic to the double bond, that accounts for its shift around 2. And so finally, the last 6 hydrogens, we'll call those E, and those are overlapping with the letter, so I'll just write it here. All 6 of those would be hydrogen E. They're all singlets because there's nothing on the neighboring carbon to split them, and they're not anywhere really 1 or 2 bonds away from a highly electronegative atom, so they don't really shift down from beyond where they would normally be expected to shift around 1. So at this point, we're just covering this now. I wouldn't expect you to be able to look at this data and formula and come up with this structure. But it should be your goal, ideally, to work toward getting to the point where you can do that. And I will tell you that if you take OChem 2 in the spring, there's going to be a lot of NMR. We're going to do a lot of reactions, not only in lab, but we'll do a lot of reactions on paper in the lecture portion of the course. And a lot of the products that you might predict, I might expect you to tell me where the NMR peaks should show. Or I might give you other questions where I'm giving you NMR data and maybe some mass spec data or IR data or a formula, some combination of that data, and expect you to draw some plausible structures. And so you can see once you have the NMR data, there's really only one structure that matches everything perfectly. If I try to move anything around here, it's going to mess up some of the splitting patterns or the integrations or the shifts. And so for all of that, all of those pieces of data to come together, the structure is very specific. And to get there, it might take you a lot of trial and error, looking at other structures and finding how they don't match. But this is the basic strategy that you should try to practice a lot so you can really master it. We'll look at the NMR data, find fragments, and then try to piece them together. Question?
Yeah. You said we don't have to be able to do that anytime soon. Does that mean it's not going to be on the exam?
It might be. Okay, so it might be on the exam for next week.
But like to that degree?
So if I gave you a question like this on the exam next week, it would be a situation where you could earn almost all the credit by coming up with some fragments that at least match the data. Putting everything together to get the final structure would be required for you to probably earn full credit on a question like that. But even if you could come up with a structure that didn't match the data in some way, so it wasn't quite correct, as long as you could explain why it wasn't correct, that would also allow you to earn almost full credit on that question. Right? So if I'm working at this and I can't come up with a structure and I've come up with some other structure that matches the formula. Maybe it's got, maybe it looks something like this. Just put something else quickly together to illustrate. So I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got too many carbons. Let's try this. Something like this. So this structure would be worth a lot of partial credit, and you could point out how some of the signals here match the data. But if you could also critique your own work, and as long as you understand the concepts enough to be able to say, well, for example, these hydrogens here would be split by this one into a doublet, so this CH2 group that integrates to 2 wouldn't give the singlet that's in the data. Instead, it would give a doublet, so you know the structure isn't correct. That's worth a lot too. So I might give you a structure and ask you whether it does or doesn't match the data, or I might expect you to draw a structure. Either way, being able to point out how the structure does match the data, or maybe where it doesn't match the data, is all worth a lot. And so you could earn a lot of credit on a question like that, even if you're not able to fully get through the entire process. Alright, so we're going to save almost all of our discussion on carbon NMR for next week. So on next week's exams, I won't put a question about carbon NMR on there, but carbon NMR is also really valuable. So probably to get a structure like this from the data, it'd be much easier if I also gave you carbon NMR data. And a couple points about carbon NMR before we finish up today. Compared to proton NMR, where almost every proton in your molecule actually is a proton and not a deuterium because of the natural abundance of that being very high, you don't need much sample to get a nice strong signal, right? So every hydrogen in almost every molecule has a single proton in its nucleus, and so everyone gives a signal and they all add together to give a nice strong signal. The carbon-13 is not nearly going to be as strong though, because most carbon atoms in your structure have a mass of 12. Carbon-12 is 99% of all carbons that occur naturally, so only 1% of the carbons actually end up being carbon-13. So you need a lot of molecules to build up enough of each molecule where there will be a carbon-13 at every center in one molecule or another to give enough signal. And so often multiple scans are taken and added together to get enough signal above the background noise. And you usually need a relatively concentrated sample. So if you dilute it with a deuterated solvent or some other solvent and it's diluted too much, then there won't be enough carbon-13 atoms in your molecules to produce enough signal to measure. The other advantage of the carbon NMR is it's usually decoupled, which means that we don't see any splitting. We just see some number of signals and where they shift. And so that allows us to really focus in on the number of unique carbon atoms in the structure. Right, so we still have to deal with symmetry. If I'm looking at the carbon NMR, for example, I've got 3, 4 total carbons here, but due to the rotational symmetry around this carbon, really I've got 2 signals, right? The signals on the end are equivalent, and the signals in the middle are equivalent due to symmetry. So you still have to look out in a carbon NMR for the possibility of symmetry, because if 2 carbons are identical in terms of their environments, they'll give the same signal appearing in the same spot, and I'll only see 1 signal for both carbons. So what's nice about the carbon NMR is it gives you a number of signals that's either the total number of carbons or less if there happens to be some symmetry in the structure. And just like in the proton NMR, the exact shift of the peak gives us a lot of information about what type of bonds the carbon might be involved in. So we're going to talk a lot more about that next time. But what we are saying here, what's nice about the carbon NMR is that the signals are basically all singlets. And so we can clearly pick out every peak is a unique carbon. So if you look at your carbon NMR from the Lab 7 data that your group may have, if you see 4 signals in there, there's 4 different types of carbons. There may be more than 4 carbons if some of them have equivalent environments due to symmetry, but you can very easily start to rule out structures that don't match your carbon NMR if the structure would give more or less signals than what you're seeing in your particular NMR. We'll definitely talk more about that next time. So practice some of this stuff, please, so you can get good at relating structures to NMR spectra. And then next time we will focus on the carbon NMR. We'll look at some examples and finish that up. And then also on Tuesday we're going to get into Chapter 9, which is about addition reactions, where you take a pi bond and you add some groups across that pi bond, to create some new sigma bonds. And so we'll look at ways to manipulate structures with some new reactions. So an addition reaction is like the opposite of an elimination reaction. There's a lot of variety there, and we'll start to get into that on Tuesday. Any questions about anything? All right then.